All right, so this video today is going to be the first part of our lesson, but it's going to cover kind of a lot. So it's going to cover four different types of what are called limacons. So before we get started, if you want to do a quick review, I don't have everything up on here, but just thought I would throw it out there. What type of polar graph does the following equation make? So if you want to run through and just name them, you can, and then you can hit pause while you do that, and then hit play and see if you got it right. And so we just want to kind of keep our vocabulary up. R equals 3 theta. This would be a spiral. So hopefully you got that. R equals 3 times sine of theta would be a circle. R equals 3 is also a circle. And theta equals pi 12ths. This would be called a radial line, is how we've discussed it. So if you are unsure of what those are, go check out the different videos on there. That would be good. But we're going to start our first kind of part of the day, which is going to be on limacons. So it's got that weird thing on the C right there. That's why it makes that kind of sound. But limacons are a type of polar graph, and we have four types of them that we're going to discuss. So I've got the structure here of when a limacon occurs. So you have two terms. You have a constant A plus or minus, and then B times sine of theta. So A plus or minus B times cosine of theta. So you get two terms, and it's not going to necessarily like normally you would think that if I do A and then plus or minus B cosine of theta, you think, well, this is a circle, B cosine of theta is a circle, but if I just add a number to it, it's going to just shift it up. So it seems like that's what it would be, but that would be if we were in the coordinate plane. But in the polar plane, when you add something like this, when you do A plus or minus B cosine of theta or A and plus or minus B sine of theta, it's not going to be a circle anymore because you're changing the radius, right? So like when you add to this, the radius gets changed and so you get a new shape. All right, so we're going to talk about what those shapes are. So we have four of them. When A is equal to B, you get a cardioid. When A is less than B, you get a inner loop limacon. When A is greater than B, you get a dimpled limacon. And when A is greater than or equal to 2B, you get a convex limacon. This one's weird. So like if I have, say, A is 5, then B would have to be like 1. So then like 5 would be greater than or equal to 2 times 1. And so it's essentially just saying that A is double or more than double B, is how it's kind of being said. So B is small and A is big, and it's double the size of B, is how you would want to see that. All right. So what I'm going to do is I'm just going to kind of walk through a way for you to kind of tell where these points are coming from, and then we're going to graph them, and then we're going to practice graphing them a little bit. So like, how are we getting them, and then how can we quickly graph them? So here we go. All right. So I got some graphs here. I don't know if they're kind of hard to read. That's a bummer. But essentially, I've got these four graphs. Like we should know how to graph y equals 2 plus 2 cosine of x. Okay, so here's the first point up here at 0, 4. And then we have a point here at pi over 2 comma 0. And then at pi 0. And then at 3 pi over 2, 2. And then 2 pi. This is 2 pi, right? So the period's 2 pi. And there we have it. So these 5 points that would normally give you this, okay, I'm going to turn these 5 points into a table of r comma theta. Okay, so I'm going to go this way because it gives me more room. So r comma theta. So the radius is actually going to be the y value. So the first y value is 4, and the angle was 0. The next y value was 2, and the angle was pi over 2. The next y value was 0, and the angle was pi. The next y value was 3 pi, or excuse me, 2 at 3 pi over 2. And the next y value was 4 when we got back to 2 pi. Okay, so now I'm going to turn these into an actual graph on a polar plane. So right, this was up here was rectangular, and this is what you're going to get if you were to graph this in polar. All right, so this is going to actually be the equation r equals 2 plus 2 cosine of theta. Okay, and this is what a cardioid is going to look like. So first, 4, 0 would be 1, 2, 3, 4 out there. And then 2, pi over 2 is going to be the vertical axis. So we're going to go out 2, 1, 2. And then 0 pi. So 0 is the radius, and we're at pi. So it's just going to be a point there. And then 2, 3 pi over 2. So 2, 1, 2. And then 4, 2 pi is at the same spot as this guy. All right, so you say all I see is basically like what looks like could be a triangle, but it can't be a triangle. So this is what it would look like if you were to put it into like Desmos. So it goes, and this is probably not the best. And then it goes like that. So it's called a cardioid. Cardioid, because it looks kind of like a heart. Okay, you know, like a cardiologist, he is a heart doctor. So cardioid is a heart. So this is 2 plus 2 cosine of theta, right? If this had been, I'm just going to throw this out there, if this had been 2 minus 2 cosine of theta equals r, then you could probably take a wild guess as what's going to happen, but it would have flipped over to the other side, and the cardioid would have been going to the left instead of to the right. So that's how you got the cardioid, okay, is when the A and the B values are the same, okay? So if I were to change the numbers, like r equals 3 plus 3 cosine of theta, or 3 plus 3 sine of theta, right? That'd be fine. I'll do a sine one just so you can see. So r equals 2 plus 2 sine of theta, right? So the first point is going to be over here. And I'll talk about y on the next page. 1, 2, 3, 4. 1, 2. And then in the middle. And so then you would get yourself this beautiful looking heart. So that would be r equals 2 plus 2 sine of theta. So you have this cardioid. It's not actually like a Valentine's Day heart. So don't make it like a Valentine's Day heart, but it has that little kind of like point. So it looks kind of like a heart, okay? Or some people said a peach in the past. So there you go. Okay, next one's pretty cool. I'm gonna do the same thing, all right? So y equals 1 plus 3 sine of x. I'm going to have my 5 points that we normally would graph, okay, from a sine function, okay. So here we have it. So r is going to be the y value, oops, and theta is going to be the x. So 0, pi over 2, right, pi, 3 pi over 2, and 2 pi, okay. So at 0, right, for sine, it's just going to be in the middle, so that's 1. At pi over 2, it's going to be up 3, so 4. Pi would be back down to 1. 3 pi over 2 is going to be at negative 2. And then 2 pi is going to be back at 1. So let's plot these and see kind of like what we get. All right, so the radius is 1 at 0. Boom. Okay, at pi over 2, it's 4. 1, 2, 3, 4. At pi, it's 1, so boom. Now this is the one where we got to think, okay, 3 pi over 2, right? 3 pi over 2 is the angle here down on the y-axis, if we were thinking of it that way. But then -2, so we're going to reflect it across the pole. So now you get another point up here. Interesting. And then 2 pi is back at 1. Oof, oof, oof. Okay, here we go. So you say, all right, I have no clue how we're going to do this. I got you guys. Here it is. Ready? This, my friends, okay, is going to look kind of crazy. So it's right here, and you're like, yoink, and it does a little inner loop. You're like, we never got the point 0, 0. No, you didn't. But here's the thing, is at some point here and here, right, which we don't know and we don't care, it does have a y value of 0. So as you can see what I did, I'll draw it again in a different color, right? I went, let's find out a good color. Let's hit up a new color, orange. All right, so I start here at this first point and I go out and around through the highest point, down and around through that point, and then it goes through, right, where the radius would have been 0. Okay, it goes through and it makes this little inside loop. Okay, so you get what's called the inner looped limacon. All right. So pretty wild, pretty crazy, pretty fun. We'll talk about how to plot those too, but that's called an inner looped limacon. That's going to happen when you have r equals 1 plus 3 sine of theta. That's what we just graphed. And that's going to happen when the a value is less than the b value. So a is less than b. And you'll always get an inner looped limacon. And the reason being is, do you notice, like, here's your x-axis on this graph? Since we ended up with negative y values, right? Negative y values. Well, if the y values are turning into the radius, right, what's that going to do? Well, it's going to cause you to reflect over the pole. And so since it's reflecting over the pole, it's not going to create a circular shape that goes down, but it's going to create this little inside loop, which is kind of cool. Okay. All right. So we have an inner loop. I'll write that. This is the inner loop. This is an example of an inner loop or inner looped limacon. Okay. All right, here we go. Next one. Same thing. Gonna get my 5 points. Got this guy. Okay. The middle's at 3, right? So r and theta. R is 5 at 0. It's gonna be 3 at pi over 2. It's gonna be, I think I'm gonna go with 1 if I can read that and do the graph in my head kind of quick. It's 3 at 3 pi over 2. And 5 back at 2 pi. Okay, so here's what I want you to start noticing about the next two graphs, right? These never touch 0. Like these two graphs, they never hit the x-axis. So that means that the radius is always going to have some value. And so this graph and the one that follows, you'll see that they never actually ever go through the center of a polar graph, right? The pole. They don't go through it because they always have some value for the radius. So if the y values are going to be all the radii, so this is all the y values, right? Y values. In this case, they're all above, okay? They're all above the x-axis, meaning we're going to get what's called a dimpled limacon. Whoa, whoa, let's check it out. All right, so first one, 5, 0. 1, 2, 3, 4, 5. 5, 0. 3 pi over 2, 1, 2, 3. Okay, pi 1. There you go. And 3 pi over 2, 3. 1, 2, 3. And then 5. These are actually pretty easy to draw. So think cardioid, but no like sharp point. So they need to go out, and they kind of do this. When you're graphing it, it's like, it's just do your best. You know what I mean? Try to make it as beautiful as you can. But as you can see, I don't do the best job. It takes a little practice, but give it a shot. So this is called a dimpled limacon, and this happens when A is greater than B. Okay, when A is greater than B. All right, so you don't get this. You get, it's like a softer point here, right? At this part, it's like a softer point. It doesn't come to a hard corner like the cardioid does. Okay, and so that's that one. All right, not much more to say about that. So you're kind of getting how I'm putting these points together. Right, just trying to have these graphed for us quickly. R over, and then theta. So we had 0, pi over 2, and 2 pi. Okay, so then the radius is 3, right? Starts up 3, then it goes down 1, so 2, and then back up to 3, and then up to 4, and then back down to 3. Okay, so we're going to plot it 3, 0, 1, 2, 3. And then pi over 2 is 2, 1, 2. Okay. And then 3 pi, 1, 2, 3. And then r comma theta 4, 1, 2, 3, 4. And then back to 2 pi. Okay, so this is called a convex limacon. And the reason it's a convex limacon, because this is r equals 3 minus sine of theta. So if this is A, right, what's B? B is 1. Don't think negative, just think 1. B is 1. So then 3 is greater than 1, but it falls under this like A is greater than 2B kind of idea. So since A is greater than 2B, okay, you get this thing called a convex limacon. What that is it's not quite a circle, but it looks like a circle. I didn't do it very good. You kind of get this like flat bottom. So essentially it's like as A, right, as A becomes bigger and bigger than B, this idea of the dimpling gets flatter and flatter, if that makes sense. And so it gets flatter and flatter, and so it kind of makes what looks like a circle, but it's not a circle because it's not centered. It actually is not circle. So we call it a convex limacon. All right, so you do have to know like when they occur, but this is why they occur, okay? This is why they occur. So you have a cardioid when A equals B. You have an inner loop when A is less than B. You have a dimpled limacon, okay, when A is greater than B. And you have a convex limacon when A is greater than or equal to 2B. Okay, so I'm going to just give you some quick pointers on how to graph these pretty easily, and then we'll go from there. Okay, so first things first, you should answer the question, what is it? So that we know what it is. So this is going to be A, and this is going to be B. They're the same. So we're going to call that a cardioid. Okay. So now if it's cosine, okay, if it's a cosine equation, then this means that it's always going to go out the furthest, right, at 0 or pi. Since it's positive, then I know it's going to go out the furthest at 0. If you think of the graph, which I do, I just don't actually graph it, but if you think of the graph of a cosine, it starts at 0, and you go up 3, right, for the middle, but then from there you would go 1, 2, 3. You would go up 3 again because cosine starts up the amplitude. So the first point is at 0, 6, because cosine of 0 is 1. So 1, 2, 3, 4, 5, 6. So what I'm saying is that since this is cosine and it's positive, it's going to go out the furthest at 0. If this had been minus, then it would go out the furthest to the left at pi. The next thing is that A is always the distance, right? That's in the opposite direction. So like if it's cosine, it goes out the furthest towards 0 or pi, which means then A is how high you go up, 1, 2, 3. Because at pi over 2, what's the cosine of pi over 2? 0. So it's just the A value. So pi over 2 is 3, and at 3 pi over 2 is 3. 1, 2, 3. So pretty straightforward. And then at pi, in this case, you would get 0 because cosine of pi is -1. So that would make it 0. So you end up with these 4 points always for every cardioid. If it had been minus, then this point that's out to the right would have been over here to the left. If it had been sine, oh no, I lost my stylus. If it had been sine, then you would have gone up or down to pi over 2, and then the A values would have gone out left and right. But now you just do your best. You pray to God that you do your best to draw a cardioid. Oh, I might have done it, guys. This could be it. This could be the greatest cardioid ever drawn. Okay, psych. It's not, but looks pretty good. Okay, so R equals 3 plus 3 cosine of theta. Hopefully that makes sense. So let's just like throw one out there, another cardioid. So let's just say R equals 1 minus sine of theta. Okay, so I'm going to start with 1. Okay, that's how far it's going to go out to the left and right. So 1 and 1. Okay, then it's going to go out the furthest to either pi over 2 or 3 pi over 2. And the furthest is actually pretty easy to figure out because it's always the sum of A and B. Look at this. This was at 6 over here. What's 3 plus 3? 3 plus 3 is 6, right? So same thing here. What's the furthest this is going to go out is 1 plus 1, which is 2. Okay, now the question is it going to go out 2 to pi over 2 or 2 to 3 pi over 2? And the answer is going to be 3 pi over 2 because it's negative there. So 1, 2, and then the other one's at 0, 0. And you just like do your best. Oh, that's kind of cute. Happy Valentine's Day. All right, so there's another cardioid. Okay. All right, here we go. Let's try this one. What is it? All right. What is it? What is it? What is it? This is a inner loop limacon. And if it's cosine, that means it's going to go towards 0 or pi, the furthest. And for us, since it's minus, it's going to go out towards pi. Okay. I'm going to say this again. The A value is going to be how far it goes in the other direction. So cosine would normally go out left and right, the furthest. So the A value is going to be 1 up and down. 1, 1. Okay. Now, this idea of A plus B is going to be how far it goes out the furthest, just to give a reason why A plus B. Remember, if I was graphing this, A is how the vertical shift, right? A is the vertical shift. Then B tells me the amplitude. So I would have gone down 3 to start, and then I would have gone 1, boom, boom, boom. Well, what's this up here? 1, 2, 3. So this Y value up here is 4. This is at like pi, comma 4, right? That's the Y value. And here is at 0, -2. Well, if I turn these into, right, if this is theta and this is R, and this is not what you want to do all the time, but But all I'm saying is this is going to be the way that you can figure out the points pretty quick, is that the furthest it goes out is always going to be the sum of the two. So 1 plus 3 is 4. And the next thing that I'll say, so it'll go out to the left because of minus. So 4, 1, 2, 3, 4. Okay. And then to figure out where the inner loop is, it's always going to be the difference, because that's how low it would have gone on the graph. So 2. So normally 0 is this, but since the radius is negative, you have to reflect it across the pole. So it would end here. So you say, how do I draw that? Oh, no problem. You go like this. Okay. Remember that when you get to here, this is where you're going to pass through the center, pass through like that. And there's your inner looped limacon. Okay. So what if it was like r equals 2 plus, I don't know, 4, okay, sine of theta. Let's do that one. 2 plus 4 sine of theta. I'll do that in blue. Okay. What if it was this? Okay, so first off, the a value, right, is 2, and the b value is 4. I know it's going to be an inner loop. All right, the furthest it'll go out is at pi over 2 because it's a positive sign. So it'll go up, and it's going to go up 6. So 1, 2, 3, 4, 5, 6 up here. Then to the left and right, it's always going to be the a value, right? Because that's what, at 0 and pi, that's when sine is 0. So it just leaves you with the a value. So there and there. Okay. And then the inner loop is going to be the difference. So 2. So 1, 2. Okay. And then we just have to do our best job. And they're actually kind of fun, like almost satisfying to draw them. You know what I mean? They're like kind of nice. And make some pretty cool designs. All right. Gonna speed it up. All right. Kind of catching on. So this is sine negative. Whoops, I didn't write down what it is. Ooh, a is bigger than b, so we got a dimpled limacon. Okay. So a is bigger than b. A is going to be what goes out to the left and right because this is sine. So 1, 2, 3, and 1, 2, 3. All right. And then the sum of the two is going to be how far it goes out because of that idea of the midline and the amplitude. If you were graphing this. So since it's negative, it's going to go to 3 pi over 2. So 1, 2, 3, 4, 5. So the sum is going to be how far it goes down. But since it's dimpled, it never goes through the pole. So that's going to be the difference between A and B, which is 1. All right. And so this is how I'm going to start it. Remember the dimpled. Oof, that was rough. That was really rough. Okay. Gonna have to work on that. But is there it is. It should not go through the pole because if you were to actually graph this like as a actual XY graph, it would never cross the x-axis. So it needs to stay away from the radius of 0. Okay. All right. Let's try one more. 4 plus sine of theta. All right, 4 plus sine of theta. So this is the convex one right here. Convex limacon. All right, because 4 is obviously more than double 1. Okay, it's 4 times greater than 1. So hopefully you can kind of guess this. So where's it going to go out the furthest towards? It's going to go out the furthest towards pi over 2. And how much? It's going to go 4 plus 1. Because at pi over 2, sine of pi over 2 is 1. And 4 plus 1 would be 5. So 1, 2, 3, 4, 5. So I'd plot this point. And we really only ever plot the points of like the 0, pi over 2, pi, 3 pi over 2, and 2 pi. Those are really going to be the only points you plot for these ones, okay? Then it's going to go out 4, 1, 2, 3, 4 to the left and 4 to the right. And then The difference is how far it would go down, like towards 3 pi over 2. So 4 minus 1 is 3. So 1, 2, 3. So you went up 5 and you went down 3, which would be the difference. And this is what you get. You just get this thing that's like kind of flat. And there you go. That would be your convex limacon. I would encourage you that after you graph each one, or if you're struggling graphing, feel free to use Desmos, kind of give you a helpful kind of vision of it. Also, another thing that could be really good would be to do the self-guided lesson again, or just take a look at the self-guided lesson and kind of walk through some of these things if they're not making sense. But these are limacons, okay? So if you want to practice, play a game, see if you just name it. And then if you want to practice graphing a few of them on your own, you can. But see if you want to name it. And then also maybe if you're just struggling with graphs, you could go to Canvas. You can go to Desmos and then put a bunch of these in there and just get a feel for how they look, and then go back and look at how I graph them and see how they correlate and line up, okay? But good luck, okay? I'm gonna fill them in. So if you want to hit pause, you can. But if not, you can watch, okay? So limacons with inner loops. I'm gonna say this one, r equals 4 plus 5 cosine of theta. That's gonna have an inner loop. R equals 1 plus 5 sine of theta is gonna have an inner loop. R equals negative 2 minus 3 cosine of theta is going to have an inner loop. And then that's it. Okay. Cardioids, R equals 4 plus 4 cosine of theta. R equals negative 2 minus 2 cosine of theta. R equals negative 7 plus 7 sine of theta. Okay. What else? What else? Ooh, missed one. R equals 9 minus 9 sine of theta. I know some of you are asking the question. You're like, yo, man, what's going on here? What's happening? It's going to do the same thing. So like this one right here, R equals negative 7 plus 7 sine of theta is going to go down, and it's going to go down towards 3 pi over 2, because if you think about it, theta, if you do theta as 3 pi over 2, that was the sine of 3 pi over 2 is negative 1. And then, oh, just kidding. It's not going to do anything. It's going to keep it the same. JK. JK lols. Don't worry about it. The negative does nothing on the A value. What a fool. All right, it's late. It's like almost 1 o'clock. Oh, it's 1:10. Good grief. And then you got R equals 9 minus 9 sine of theta. Okay, dimpled limacons. I got this. R equals 6 plus 4 sine of theta. And R equals 5 plus 3 cosine of theta. Yo, let's go. Then R equals 6 minus 2 sine of theta would be the convex limacon. Whew. Oh my word, there it is. That's the ball game. Okay, they're really not that bad. They just like take practice. Okay, so practice. Got an assignment there. Also, just mess around with Desmos too is a good way to get some practice in. All right, talk to you later. Have a great day.